Hi, everyone. What today's topic is going to go through, we're going to go through 4 problems, and it's just 4 problems. We're going to deal with them relatively quickly. This video is an extension of Polynomial Inequalities 1. So I would absolutely not be attempting this if I have not worked my way through that theory. So let's take a look at number 1 that you have on the screen, and I just want to play around a little bit with where some of this stuff can go and how you can see it in some slightly different ways. So question 1 says, for what values of x does the graph of f of x equals, and then there's your cubic, lie above the graph of g of x, and there's your quadratic. I'm just going to shrink that down now to make sure that we can kind of have some space to work a little bit. And there we go. And so I think the first instinct for some people may be, oh no, now we have some graphs and we don't have to, but I wouldn't be worried about that whatsoever. Yes, you could solve this problem by trying to look at it and say, okay, so I've got a set of axes, I have like a parabola that exists somewhere, that's my g of x, and then I have this like cubic that maybe looks like this. And yes, you could, if given with those pictures, figure out, well, where does, my red curve lie above my blue curve? And you could then state those solutions. Yes, you could do that graphically. However, I would argue for anyone that I don't think that should be your default. Instead, we can deal with this as an algebraic problem. If a graph lies above the other graph, then it has a higher y value than the other graph. And y values are the value of the function. So really what this question is saying then is it's saying, when is f of x greater than g of x? That's all. And so we can make this a purely mechanical problem. And now we could go ahead and now we see that we have 4 terms. I could factor by grouping. I could now pull out my common factor. And I come in on that. Now, you get to that point and you are free to use an interval chart if you want. But I'm hoping that instead we could say that x equals -1. We know that that's our roots. We don't get any roots from the factor x squared plus 1 because that can never be 0. And so now we have a quick set of axes. We know that we only have this one root at -1. Now, if we put everything together that we have at our disposal, that original function has a positive leading term, which tells you that it goes off to the right forever and up. The only root that it has is -1. And that root only shows up once. So I'm going to cross like normal. Like maybe that's what my graph looks like. You shouldn't even be concerned if it's a really accurate sketch to that graph. Who cares? For the purpose of the inequality, we have that. And so when the question then says, when is that positive? We know then that that solution is anywhere to the right of -1. And there you go. So the common tendency is as soon as you see the graph of something, then we think we have to deal with it graphically. No, this is an instance where you can go through algebraically and you are good. Okay, let's tackle another problem. When you take a look at problem 2 asks you to write an inequality that has each solution. And so if you just look at problem A, we need to write an inequality that has the solution to the inequality -3 to 0, and then greater than 2. So I just want you to imagine that this would be an instance where you would go through a bunch of work, wrap back up to the other top, through a bunch of work, and at the end you would say between -3 and 0, greater than 2. That's really the context of the problem. Okay, so how can we go about trying to solve this? Well, first off, now that you understand what the question's asking, I want you to pause on this one. Okay, I want you to pause. I want you to go through and I want you to imagine trying to create an inequality that has that as a solution. And then we'll come back and we'll talk strategy. Okay, pause it now. Okay, and we're back. So my suggestion to you in this instance is if at some point we wanted to be able to state -3, blah, 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 then you would have taken that solution from a picture. In all likelihood, that's where you would have taken it from. And so my recommendation to you would be then, well, then why don't we build a picture that has that as a solution? So I'm just going to get rid of kind of that rough set of axes because I want to make it a little more formal. I'm going to now include a decent set of axes, and I am going to draw a picture that would have that as a solution. Now, here's the other part. Take a look back up in the question, and it says write an inequality. Notice it doesn't say write the inequality. Had it said write the inequality, then that means that there is one answer. It says write an inequality. That implies that there are multiple answers, and there are. So we have some choice here. The only thing that we don't have choice on is we know that our graph has to hit the x-axis at those values. We have those from the original intervals. Well, now we need to draw a graph that satisfies that. So I just need to pick, do I want my graph to be above or below the x-axis during those intervals? So I'm just going to pick above. It doesn't matter what I pick, but I will pick above. So between -3 and 0, I'm above, and greater than 2, I'm above. Okay, well, now that I've picked that, like my graph would probably look something like that if it was to continue to fill in the gaps. Okay, I think that I can actually build an equation that would represent something like the blue. If I have those x-intercepts, then I know that I have to have these factors. If I have an x-intercept of -3, then it must have come from a factor of x plus 3. If I have an x-intercept of 0, it must have come from a factor of x. And if I have an x-intercept of 2, it must have come from a factor of x minus 2. That would be all of my factors. Now, my only decision then was up here when I chose to draw my graph above, then I know above is greater than 0, so my inequality is greater than 0. Now, the only last thing that we have to consider is take a peek back up at our original and notice that what we had in those original intervals was that it could also equal 0. So I have to ensure that the inequality I created also allows for those values to be equal. And therefore, as long as I make sure that I've included a greater than or equal to, then I've included everything I need. Don't waste any time going through and expanding those brackets to collect like terms. You leave that thing in factored form and you are good. Okay, let's try another one of these. Okay, I just gave you a different form of your solution. So now I've stated that x, and for anybody who doesn't recognize that kind of soft E symbol, that's just the element symbol. So x is an element of, which just means that x is a part of those intervals. So I want you to pause the video now, and I want you to work your way through this one. Okay, we're back. So I'm going to construct this the exact same way. Set of axes. I can tell from my solutions that I have to have an x-intercept at -4, an x-intercept at -1, and an x-intercept at 3. Now, just for variety's sake, last time I chose above. This time I'm going to choose, yikes, that just jumped. I am going to choose below. So within those intervals, I'm going to always make sure my graph is below. So from -infinity to -4, I'm below. From -4 to -1, I'm below. And 3 and greater, I'm below. Well, now that would be the rest of my graph. And I get something like that. Okay, let's go ahead and build our factors. An x-intercept at -4 must have come from a factor of x plus 4. My -1 must have come from x plus 1, and my 3 must have come from x minus 3. I chose below, so therefore I have less than 0. Okay, there's a couple key things that we've got to take a peek at, and this is where we need to make sure that we're good. Are you guys okay that function, not inequality, just what I've boxed in green, that function doesn't match my graph? Okay, there's a couple key things that we have to make sure we take care of. So the first thing is, when you take a peek, we notice that we are tangent at -4. And we know from multiplicity of roots that that means that that factor of x plus 4 must have shown up multiple times. So it doesn't matter what exponent you put on x plus 4 as long as it's even. Okay, the second thing, notice that my graph goes down forever to the right. But that function that I've created, if I expanded it, I'm going to have a positive leading term. Positive leading terms going up to the right. So I have to make sure that I include a negative constant out in front. So I'm just going to pick the easiest one, -1, to ensure that that is a negative graph forever to the right. Now I like my solution in blue. Okay, so see if we matched up and we're good. You'll also notice as a little confirmation, for anyone who chose above to construct their graph, you're just going to get a rearranged version of my blue equation. You're going to divide out that negative, and that means change the sign of the inequality, you're above, and you should have come in on this as your inequality. Okay, hopefully we match up and we're doing well. Okay, and so now I want you to just give problem 3 a read. Problem 3 is a pretty quick read, but I want to make sure that we're good with it. So let's take a look at what the question's asking. It's asked us to find the solutions that satisfy both the first inequality and then the second inequality. So we have to find solutions that satisfy both x squared plus 4x minus 5 is greater than 0 and x squared plus 6x minus 7 is less than or equal to 0. So what I want you to do, pause the video now and see where your gut takes you. Work your way through as much as you can. Come back when you get stuck or to check your solution. Okay, pause it now. Okay, and so we're back. I'm just going to shrink that down to make sure we got a little extra space. Okay. My strategy to you, my advice to you would be almost treat these like it was a system of inequalities, which is what it is. That is, I'm just going to put like a little 1 and a 2 so we can talk about them as inequality 1, inequality 2. And if I was to go through and solve each of those individually, then I could start to examine the solutions of them individually to try to see which ones satisfy both. So I'm going to take that first inequality and I'm going to go through and I'm going to say, okay, so if x squared plus 4x minus 5 is greater than 0, then I can factor that. And I then know that x equals negative 5 or 1 are my roots. That I could then draw a quick picture, know that negative 5 and 1 are my roots. That is a parabola that's opening up, so that means I have to go through here. When is that parabola positive? Well, it's positive everywhere to the left of negative 5 and everywhere to the right of 1. Okay, I have solved the first inequality. Now what I want to do is go ahead and solve the second inequality. So I'm going to do the same thing, and I'm going to solve inequality 2. That x squared plus 6x minus 7 less than or equal to 0. I'm happy that that one factors as well, and so therefore I get x equals negative 7 or 1 as those roots. So if I were to draw my picture of that parabola, then negative 7 and 1, it's still a parabola opening up. That my solution to that inequality, when is it less than or equal to 0, would be between negative 7 and 1. Because it's equal to, I have to make sure that I've got my square brackets to say I can include it. So what you have now is you have the individual solutions to each inequality. But I haven't addressed which solutions satisfy both. And so now what I'm going to do is I'm going to jump up onto the right, and I'm going to work through the both aspect. Some people could just look at those two green statements, and you can go, okay, so the first one, my x values are less than negative 5 and up 1, and my other ones are in between. Yeah, okay, I can see which ones work. But I'm going to argue that the vast majority of people can struggle to see that. And so my suggestion to you would be the same as what it was before. Draw a picture. Except the picture that I'm going to use is going to be my good old number line. So what I'm going to do in blue is in green, I'm going to put on the solution to the first inequality. Negative 5 would be here, 1 would be here. I am everywhere to the left, and I have everywhere to the right. Now what I'm going to put on in red is going to be the solution to the second inequality. That I am down here at negative 7 and up here to 1. And now I have to be a closed circle here and everywhere up to my closed circle here. Now that I have the picture to it, I have to answer the question both again. That means and. So I need both. So I'm simply looking, where do the red and green lines both exist? And you'll notice if I just start left to right, well, both the green line and the red line start at negative 7 and include negative 7. And I keep seeing red and green lines until I get up to negative 5. I notice that the red line occurs there, but the green does not. It's an open circle. And so I go all the way up to negative 5, but not including it. After that, I see just the red. At 1, I don't have both. Notice at 1, the red occurs, but the green does not. And then everywhere after 1, I only have my green occurring. So what you see in purple then is my final solution. Any x values between -7 and -5 make both of those inequalities true. And there we go. So, a little bit of a quirky problem for us to be able to work through. Notice, though, your strategy. To be able to answer that, we solve them individually, and then just consider the both case at the very end. So, hopefully not too painful. There's your stuff for today. The extension of Polynomial Inequalities 1 kind of gives you an idea of where we can go with it. Okay, jump in, knock out some practice. Best of luck.